Hi, my name is Relational, and today I'll be giving you a presentation on bringing relational lenses to Haskell. Before we start, I'd like to give a quick recap on bidirectional transformations. In particular, let's talk about lenses. With lenses, we normally consider two data structures, A and B, as well as two transformations between them. The forward direction we call get, and takes an A and gives us back a B. And more importantly, in the reverse direction, called the put operation, it takes an A as well as an updated B and calculates an updated A. Consider the example of a point class with two coordinates, where we can define a lens with a forward direction get that returns the first coordinate, as well as a put direction that takes a point as well as an updated coordinate and returns an updated point with the updated coordinate. So now on to relational lenses. Relational lenses were originally introduced by Buchanan, Pearce, and Vaughan, and bring the concept of lenses to relational databases. So when talking about databases, we normally consider a structure with many tables. And when programming with databases, we're normally only interested in a small view at a time. A view is a collection of records with the same type. With relational lenses, the get direction calculates the view from the database. And what we'd like to be able to do is to make changes to that view and then submit the updated view so that it updates the database at the relevant places. And this is essentially a programming languages-inspired solution to the view update problem. The original work of relational lenses rematerializes the entire database in the put direction, which is quite an expensive operation. But existing work on incremental relational lenses generates a delta of the table and just applies that delta to the database. But we won't be talking about semantics today, and instead we're focused on language integration. So where would relational lenses typically come in use? Let's consider a typical model view controller application with a web server, a database server, and a client. The client would like to perform some operation on the database, and so it would request a view from the server, which would then forward that request to the database server in the form of a query. The database server would then instantiate a view and send it to the server, and the server would just forward that view to the client. Especially with modern-day rich web applications, the client can execute client-side code and perform all sorts of changes to generate an updated view directly. This updated view can then be sent back to the server, which would now like to update the database server with any changes made by the client. To do that, the server then calculates a delta over the original database, which can then be applied to the database server. We're now going to introduce relational lenses using a simple example. Let's implement an event ticketing system. So let's assume that we're hosting an event, say the Haskell Symposium, and we'd like users to be able to register their attendance. So in this case we have Mike, and Mike has all of his friends. And Mike would like to create a reservation with 4 tickets for himself and all of his friends. And each ticket should be linked to a user object containing further information about the user, including their name. The first task that we need to do is to connect to the database server, and this is done using existing libraries for PostgreSQL. And in doing so, one has to provide the usual connection parameters. We would then like to create an events table. To do this, we declare a primitive lens on a table called events. And we, in addition to the name of the table, we also provide it with a record type, as well as a set of functional dependencies. The record type in this case contains two columns, the event ID as well as the event name. And the functional dependencies require a functional dependency going from event ID to name, which essentially says that the event ID uniquely identifies the event name. If we then call setup, we can automatically create the table in the database. We'd now like to put some data into the database, and to do that we call put, giving the lens a set of records. In this case we give it 2 records, one with the Haskell symposium and one with ICFP. If we subsequently call get, we'll get the same records back as we just supplied it to the put direction. We can then go ahead and declare the table reservations. In this case, we assume that the reservations table already contains 3 reservations, 2 for the first event and 1 for the second event. We can now go ahead and do something a little bit more interesting. We define 2 tables. The tickets table contains 2 columns for the reservation ID as well as the email address. This table doesn't require any functional dependencies. We also define the table users, which has 3 columns, one for the email address, name, and title. This table requires a single functional dependency going from the email address to the other 2 columns, specifying that the email address uniquely identifies a name and a title. We can then define user tickets as a relational join between these 2 tables, essentially assigning user information to each ticket. On top of that, we define the select lens res view so that it filters out all tickets belonging to a single reservation. We then set up these tables and populate the tickets for reservation 1 with a single entry for Mike, who has the email address mike@mail.com as well as the title Mr. We can then go ahead and simplify this even further. We'd like the user to be able to enter a list of email addresses. To do this, we first define a lens over the users table, which specifies that the columns name and title should be dropped, using the default values unknown at NX. These values are used when no existing record can be found and a new entry has to be created. We specify that the dropped column should be matched against an email address. Using the new lens, we define resViewSimple as the join over the tickets lens and the new users lens. And on top of that, we apply a select lens to filter out all tickets belonging to a single reservation as done before. Using this lens, we can define the function setResEmails, which attaches the reservation ID to each email, and then calls put on the underlying lens. We then call setResEmails on the second reservation, providing it the emails me@example.com as well as mike.mail.com. If we now call get on the full reservation view lens, it'll yield the previous record for mike@mail.com with his existing user data of using the title Mr. and the name Mike. For a previously unencountered email address, me@example.com, the default values are used. This was our example. We'd now like to go over a few details regarding lenses. We say that lenses are well behaved when they satisfy 2 conditions. The first is if we call get after calling put, then we should get the same structure back as we put into it beforehand. The second is that if we call put without making any changes, then the underlying initial data structure shouldn't be changed. For relational lenses, quite a few conditions are required for well-behavedness. Examples of this are the linearity of tables, where we're only allowed to use a single table within a lens expression once. There's also many restrictions on predicates, and quite a few requirements for functional dependencies that have to be ensured before they can be safely used. We also have to ensure consistency to make sure that things like predicates are well-typed with respect to the columns. These well-behavedness rules were originally specified by Hannon, Pierce, and Vaughan, and then revisited in a functional programming language setting in the paper Language Integrated Updatable Views. The only publicly available relational lenses implementation we know of is within links, and the existing implementation shows how incremental relational lens semantics can be implemented, as well as how relational lenses can fit into a functional programming language environment. The existing implementation essentially extends the compiler with relational lenses, making them a hard-coded feature. This requires quite a heavy implementation, with changes to the parser, the type system, the intermediate representation, the interpreter, etc. And this makes it fairly difficult to maintain, even if it gives you full flexibility to implement whatever is required. And this can also pose compatibility issues, as other language features need to be aware of the existence of relational lenses in order to ensure that they don't break. Instead of having to extend the compiler with relational lenses, it would be much nicer if it was possible to implement them as a library. The problem is, relational lenses have a lot of static checks are required, and these really should be checked during compile time to ensure that nothing breaks when a program is running. We generally like to avoid feature-specific code in the compiler. This makes it easier to implement other great features because whatever the compiler provides is more flexible to use elsewhere, and it also results in cleaner abstractions for the intended feature. Relational lenses make heavy use of Haskell's type system for computation. In particular, relational lenses make use of type literals within the language. This allows us to store strings, numbers, as well as custom data types in type variables. We can also use type families to define functions. The example shows a type family for calculating the length of the list. We also use type classes in order to generate code or dynamic values based on a type. And finally, we make use of Haskell's constraints for defining type-level checks. Constraints can either be equality constraints, checking whether two type variables are equal, or type class constraints, ensuring that there's an instance of a specific type class. We will now look at a few examples of where type-level computation is used to implement relational lenses. As mentioned before, a table can only be used once during a lens expression. In the example above, the tickets table is used twice within a single lens, and we would like this to yield an error to the programmer. In order to implement this, we want to define a constraint, table disjointness, which ensures that this doesn't occur. We store the tables in a type, and the type is of kind list of symbols. We can then define a type family is disjoint, which determines if two lists are disjoint. This assumes the type family is element, which checks that an element is contained in a list. Using is disjoint, we can define tables disjoint, which ensures that the result of computing is disjoint between two sets is equal to true. Relational lenses are used to handle relational data, and so we need a way to represent views as well as tables and records. We consider views to be a set of records with the same type. The example shown is a collection of records with columns reservation ID of type integer and email, title, and name, all of type string. The kind of a record is a list of symbols mapping to types. The star represents the ordinary data kind within Haskell. The example shows how to declare a record with two columns, A and B, both of type string. And we show the equivalent construction of the actual data type used to construct it, which is two cons applied to an empty. We also show a few example operations performed on the lenses. For relational lenses, we require the ability to execute relational algebra operations on records. We show here how to implement the projection operator. To do this, we first require a type family, lookup type, which looks up the type of a column in a row type. We then declare a type class, which uses the type family to construct any desired projection. We represent tables using sets of records, and implement relational algebra operations such as projection on the entire table. Lenses must also track functional dependencies statically. An example is a constraint that requires the unique title and name for each email. Relational lenses requires functional dependencies to be in tree form. And tree form essentially means that the functional dependencies form a forest with just disjoint nodes. The example on the right shows a graph which is not in tree form. In this particular case, it contains the edge D to A, which breaks the acyclicity check. Functional dependencies are defined as a data type, and the constructor takes two lists of symbols. We also define the infix arrow operator, which sanitizes the data by removing duplicates and sorting the columns. An example of defining a functional dependency within Haskell is shown below. Using this, we can define the tree form check in a fairly straightforward fashion. I won't go into details of the implementation, but the top-level tree form definition is shown on the slide. In the example shown, we also throw a user error using a custom-defined function, OKOError, when the functional dependencies are not in tree form. We also make heavy use of type-level computation for predicates. We define a small DSL constructing predicates, and when constructing predicates, we retain a large amount of information on the introduced predicates statically. We show an example of how to construct a predicate for the query test is equal to 5, as well as the type that the predicate would then have. In the previous predicate, all of the predicate was known statically, and this is sometimes required so that all type checks can be performed. In some cases, though, we may also want to be able to produce some predicates dynamically. And luckily, not all predicates need to be fully statically known for all the type checks to be performed. In this case, we show an example of a predicate which depends on a bunch of runtime values, and where we only retain the type of the predicate, which is sufficient for some checks to be performed. We will now look at how the lens data type is defined. We start with the lens refinement type, which we call the lens sort. The lens sort has 4 components: the set of tables used, functional dependencies and predicates that apply to the view, as well as the record type. We define individual accesses for each component, and also make use of helper functions such as query row that return the record type. Using the refinement type, we can define the actual lens type. The lens data type has a single argument for the lens sort, and a constructor for each lens type. We start with the primitive lens. The primitive lens takes a table name, a record type, as well as a set of functional dependencies. And it constructs the sort by using a singleton list of the supplied table name, as well as the record type and set of functional dependencies supplied by the user. The predicate uses the default predicate, which is true. The example below shows how the primitive lens for the lens table is defined. We now look at the select lens. The select lens takes a predicate as well as a further lens and returns a new lens of sort sNew. The sNew sort is constrained by the selectable constraint, which will be shown on the next slide. The example below constructs the lens by giving it the predicate, as well as the underlying lens. The selectable constraint consists of a few parts. The new sort is defined as the old sort except for the fact that the predicate should include the additional predicate supplied by the user. Selectable X contains all constraints which are required for correctness. This includes a check that functional dependencies are in tree form, the predicate should type check, as well as further type classes required for the implementation. There are also some common constraints which are required by each lens and are solved by solving the lens common constraint. The additional lenses drop and join are defined in a similar fashion, and we don't go into further details here for brevity. So to conclude the presentation, no further extensions to Haskell were necessary for this implementation. In fact, there's many great existing libraries out there that make use of Haskell's type-level computation abilities. There's lots of existing work on type-level records, and they even have more features than ours does. This includes the ctrex and row types packages. The type-level sets library was also helpful for our implementation. There's still lots of future work to be done. The current error message handling is very basic, and it would be nicer to throw more detailed errors when things go wrong. This is something that Haskell already supports, but just hasn't been implemented yet. The constraints generated are currently also quite large, and it's unclear if this can be improved. It would have been possible to simplify them a bit using a dependently typed system, but it might also be possible to just use better abstractions for this. Currently we only support PostgreSQL, and it would be nice to support other database drivers, but this should be fairly straightforward. There also isn't any support for serial columns yet. So to sum up, we were able to implement relational lenses in Haskell as a library. The current implementation supports the incremental relational lens semantics and uses roughly 3,000 lines of code. And this provides an easy-to-use view update for relational databases in Haskell. Thanks for listening, and I'll now be taking any questions.